Welcome to the Maniac Talk series. Today's speaker is Gail Jackson, and she's a falling snow detective. And for those of you who do not know what a falling snow detective is, I would have loved to explain it to you, but I don't want to ruin her talk, so I won't be able to say anything. But I can tell you a thing about Gail. She's the GPM Deputy Project Scientist, and in her daily activity she deals with a lot of precipitation science. Not only snow, all types of precipitation, but snow is obviously her favorite.
Thank you. So, yeah, I'm going to talk about falling snow, and I really like the title of my presentation that actually I did not come up with. But my role is to take satellite measurements and interpret what's falling out in terms of snow at the surface. So you have to look at all the different clues. You have to look at the clues as to what is the satellite seeing, what's in between the satellite and what's falling at the surface, and then how do you interpret all these different measurements? So you have to use all these different clues. So I like the idea of being a snow detective. And I'm going to talk to you today about how I got here, my path from childhood to here, and some of the work that I'm doing, and why it's important to look at snow. I want to acknowledge my collaborators and colleagues that have helped me with this work. I have both snow people, my snow science people, as well as GPM, and I'll talk about the role of GPM here. I love snow. I don't know if it was because when I was one, my parents moved us from Wisconsin down to Florida, and I never got to see snow again. But snow, it just fascinates me. Everything from the beautiful symmetry and yet the fractal nature of it, the fact that it provides water resources for all life on Earth. Yes, you get rain, but snow is the kind of precipitation and water resources that lasts over time, that doesn't just run off. Also, snow is beautiful. It's beautiful. You stand out in a snowstorm, and those snowflakes, they just come fluttering down and swirling. It's almost like they're dancing down from the sky so that we can enjoy them. I just really like snow. And about 10 years ago, a colleague of mine, so let me do a little back step here. I had been looking at ice above the melting layer. So you know clouds have ice and then they start to melt and it turns into rain. I had been looking at the ice up there. And a colleague of mine, Jim Weinman, who has passed away last year, this guy right here, came up to me. He said, "Hey, Gail, I got this great idea." Now, Jim has a lot of good ideas. Sometimes I work, sometimes I don't. He said, "Gail, can't you take and just use the snow above the melting layer and estimate how much snow is falling at the surface? It's just like a cloud with no melting layer, no rain." I'm like, yeah. So I ended up going down this path, and it's actually a really small field. There's probably only about 100 people worldwide that are looking at falling snow estimates. So I am forever grateful for him to come up to me and give me one of his good ideas. Okay, so I'm going to talk about some interesting facts about snow. I'm going to talk about my path to becoming a snow detective. I'm going to talk about who cares, why should we measure snow, and how can we measure it on the surface, how can we directly measure it, how can we measure it from space, and then I'm going to summarize. Okay, so between each one of these topics, I have a quote. As I said before, I'm going to talk a lot about GPM, because GPM is one of the satellites that's the first ever to design specifically to measure snow. There are satellites that can see snow now, but they were not designed for that. People have been interested in snow for many, many ages, and you'll see some quotes throughout my talk of different poets and writers that have expressed their joy and their thoughts about snow. But I want to talk now about some facts about snow. Did you bring your scissors? Okay, I have some snowflakes. They're being passed around now. They're little triangles. There's a few that have no pattern on them. These are no pattern ones. And there's a few that have patterns. The goal is to cut out the white part so that only the black part remains. Okay? There's probably enough in here for you guys to cut out 2 or 3 of them. So you'll cut out the white part, and then there's a little bit of tape on the black part that you have to kind of separate. If you have long fingernails, it works very well. And then the little black piece comes off, assuming you didn't take one without a pattern. And then you just carefully unfold it. And what we're going to do here is we're going to use these a little bit later as part of experiments during the talk, because I know you guys are already totally bored with my presentation and you need something to do with your fingers. I'm going to make you stand up too a little bit later with these. So if I can. Okay, you cut out the white part. Cut out the white part of the pattern. Or you can cut out the black part. I don't care, it doesn't matter, it'll work. And then you'll get a snowflake something like this, okay? And be nice. If your partner next to you does not have a pair of scissors, share your scissors. And then also, please, please try to clean up after yourself, because I'm going to have to vacuum the floor afterwards otherwise. Okay? So, and all of these are from this book, Snowflakes. You can find snowflake patterns just about anywhere. So, cut those out. Pay attention, but cut those out. Okay, so interesting facts about snow. Have you ever thought about the fact that water can be clear? If it's in a lake or a glacier, it's blue, but snow is white. It's all water, right? So one of the very interesting facts about water is that based on the properties as it forms as liquid and as frozen, the incident radiation, like the sunlight, will scatter or absorb differently. So what happens for water is there is no absorption nor reflection, so it looks clear. The light just goes right through it. When you have snow, it reflects and scatters equally, and therefore it's white. That's actually my daughter peeking through there. And then for glaciers or for lakes, what happens is that, so you know your eyes, they see colors based on the wavelengths coming in. So what happens in glaciers is that the red color, the red spectrum, is absorbed by the thick ice or the thick lake water, and all that's reflected back is blue. So it's very interesting. I think this is a very interesting fact about snow and water. Why is frozen water or snow so interesting or scientifically interesting? It's the hydrogen bonds. So you have an oxygen molecule and some hydrogen molecules, and they form the water, H2O, and then there's this bonding that goes on. And what's fascinating about this is that for liquid water, these bonds, they kind of like, they join and unjoin, and they always are changing, they're always moving. It's kind of like square dancing. If my body was the oxygen molecule and the hydrogens were my 2 arms, you're constantly moving around like in a square dance. So these water molecules are constantly linking arms and then unlinking arms and moving around. And that's one of the unique properties, is because they're always joined, but they're always moving around. But for frozen water, what happens is that the hydrogen molecules, basically it's like your arms get straightened out. So you can join hands, and you can only join hands with a few other partners, so you make a 6-sided thing. And you can move a little bit like this, but you really can't like unbreak your bonds. So you have to keep your hands held and your arms straight for frozen. So what that allows then is that there's this open extra space here that makes the ice less dense than water, and that's one reason that it floats. And it also helps to insulate. You've heard of igloos. They insulate because of the properties of ice. All right, shout it out. How many sides do snowflakes have? All right, I heard a few 6s. 6 is right. Oftentimes, I think even Google has shown like 8-sided snowflakes. They're never 8 sides. It's always because of this hydrogen bond that you saw those 6-sided bonds there. So that's always 6, and again, it's because of the structure. The reason that you can pour water is because those bonds, they attach and detach, but they always stay together, and so that's why water flows. Interesting fact about snow. I often go, well, I don't often go, about twice a year I go to classrooms, school classrooms. And one of the questions that I always get, is it really true, Dr. Jackson, that there are no two snowflakes alike? And I have to say, you know, when you look at them overall, so if you pick up some of your snowflakes that you're cutting out, you know, some of them started with the same pattern. So macroscopically, in the large scale, they may look alike. Like down here on the bottom, you know, some of these look very similar, but they're all slightly different on the microscopic level. When you cut these out, you and your friend that may have a same pattern may have just a slightly different way of cutting them out. So microscopically, they're different. And it's the same way with real snowflakes in clouds, because they go up and down in downdrafts. They might be exposed to different winds. They might be exposed to different temperatures and water vapor, and so they collect differently, but they all have 6 sides. Okay, so my path. How did I get to where I am? I told you a little bit about Jim Weinman, but I'm going to step way back and talk about growing up in Florida. Okay, so Florida is mostly known for hurricanes, right? You know, you don't think about snow like that. So this is actually an image of hurricanes from 1970 through 2011. I pulled the 2 red ones here, or yellow ones. Those are actual hurricane category 1, category 2. All the rest are tropical storms. You know, when I was growing up, I thought we had lots and lots of hurricanes. It turns out we had a lot of tropical storms and about 2 hurricanes. So these were the 2 hurricanes. I sort of remember this one. I mostly remember it because it's my grandmother's first name. Agnes was her name. So my parents talked about it a lot. Kate was right before I left, and I definitely remember this one because in Tallahassee, lots of trees fell over. You know, like locally we've had some trees fall down in recent storms. Well, Tallahassee had not been subject to heavy winds in many, many years, and so lots of trees fell down, lots of power, lots of houses needed to be replaced. But I certainly remember all these tropical, well, not all of them, but lots of the tropical storms, because they would come through and they would rain for a couple days, and there'd be lots and lots of rain. Okay, there's one snow that I remember. Okay, and looking at the snows, I was only in the area until about 86 or so. This snow is the one I remember. A measly 0.4 inches. They closed down schools. They told nobody to drive. You know, it was like the world has ended. But I do remember that one. That was great. I had already left by the time they had gotten this 1 inch here. But they do get a lot of snow. This is actually an image from 1899. Tallahassee's the state capital, and the Congress people there are throwing snowballs at each other. So they do get snow occasionally. More snow than 0.4 inches. Okay. This is a picture of my family when we were younger. This is me. My father was a physics professor at Florida State. He was a physics professor for 40 or so years, 45 years. My mom started as a nurse, and then once she started having kids, she was a homemaker. And once my younger sister got into school, she said, okay, enough of this. I'm going back to school. I love marine biology. I'm going to get a marine biology degree. She did that, couldn't get a job. So she went back to school and got a computer programming degree and worked for the state of Florida for many years thereafter. I have 2 brothers and 1 sister. My dad, he pushed so hard. He wanted all of us to go into physics. We all said, no way, no how. But somehow he convinced us all to go into engineering. So all of us have some sort of engineering degree. The last thing I want to point out about this image, if you look at my dad's hair, prematurely gray. It runs in the family. So I blame him for my gray hair. Of course I could color it, but I'm not going to do that. Okay, so I got my electrical engineering degree from Florida State University, my bachelor's degree. And I was, you know, I started out in computer science because my mom had just finished her programming degree. And I thought, well, you know, computers are kind of a new thing, and I'll try that. And about the middle of my end of sophomore year, I said, you know, I just don't want to sit in front of a computer every day, all week long. I don't want to do that. So I said, well, electrical engineering, I can build things, I can do really cool things. So I switched to electrical engineering. But I didn't really know exactly, I knew there were a lot of military applications for electrical engineering. I didn't want to do that, but I didn't know what I wanted to do. So I ended up taking this elective, you know, one of those, I'm going to make an A because this is such an easy class. And it was kind of, it had an interesting title, Disaster Planning for City Managers. The professor in one of the lectures showed just a still image, like this is a moving thing, but he showed a still image. And that was my eureka moment. I said, I want to do remote sensing of the Earth. That's what I want to do. I had already decided I was going to get a PhD because, I don't know, my dad. So anyway, I started doing that. So I went to Georgia Tech. I got a master's degree in electrical engineering. At the time, there were no professors there doing remote sensing of the Earth. There was one that was doing remote sensing of planetary atmospheres. I'm sorry for my space science friends out there. I really like the Earth and the touching, the feeling, and being outside, so I really wanted to do remote sensing of the Earth. So I ended up working for a few years at Bell South Services. And then Professor Al Gajewski came to Georgia Tech, and he was doing atmospheric remote sensing. And the dean of the school convinced me to come back and go to the school and get my PhD. So this is actually a photoshopped image. You can tell this guy's added. These are all of the students that Al Gajewski graduated before he left to go to Boulder. And all of us are still related to this field. Jeff Pietmeyer works over in Code 555. He's an engineer over there. Dave Kunke worked with NPOS and the microwave imager sounder. He's at Aerospace, and he still continues to do work even though NPOS has changed names a couple of times. This is my husband. We met before we started working with Al Gajewski. He did not know that we were dating, but that's okay. He's in the intelligence community, but because of his background, the intelligence community is actually very interested in national security issues in a changing climate. So every once in a while, he's pulled into committees to talk about such issues. Okay, so my family life now. This is my family. Ooh, I see a beautiful snowflake back there. Okay, I have 2 kids. My daughter is almost 17 and my son is 14. We like to take cool vacations. We like to take cool vacations wherever mommy is having a business trip. So this is Hawaii, and it's a conference that I went to in 2010. This is actually just me. It's in Zugspeit, Germany. We had a meeting up there because we're studying snow. This is a side trip in Mont Blanc from one of my Germany trips. We did a short hike around Mont Blanc. We like to go local trips too. This is just the capital. This is a Canadian trip. And I put this picture of me caving because I actually met my husband caving. And it kind of goes back to the theme that I love the Earth. I want to be outdoors. I like to hike. I like to know what's happening with the Earth system. Okay, so my work as a scientist here at Goddard. As mentioned in my introduction, I'm the Deputy Project Scientist for GPM. This picture shows mostly engineers. There's a few scientists in there. I'm there, and I think Dahlia's in here somewhere. So it's a really big program. GPM is being built here, and I'm going to talk a little bit more about it later in my presentation. As I said, I get to go to cool places. Cool places. This is Finland in February. This is me. It was cold. Do you think it's cold out there now? It was really cold in Finland in February. This is a Canadian field campaign, and I'm helping to launch a radiosonde balloon. So I get to do some really fun and interesting things. And I get to detect snow, whatever means available. Okay, so this is a little bit more about the GPM mission. Some of you already know about this. We are building a core observatory here at NASA with JAXA, the Japanese, as our partner. And this has 2 instruments on board. One's a radar, one's a radiometer. I'll talk about those more later. Using this core, which has very, very advanced instruments, we'll be able to use it as a reference standard for all of these other satellites of opportunity that are being launched by other partners. putting all this data together, we get precipitation every 3 hours globally. And so what this allows us to do is to use this data in science and societal applications. Okay. So why do we care? Why would anybody care about snow? Yeah, we care about rain because, you know, it can water our crops and things like that. Well, there's a couple of reasons. One is because of the water resources. And, you know, some of you know that of all the water on Earth, 97% of it is salt water. So you really can't drink it. So the rest of that, about 3% is fresh water. Of that fresh water, about 70% of it is in glaciers or locked up in permanent ice. So there's a very small amount that's in the atmosphere, that's in the lakes, that's in the aquifers, that is easily available for freshwater resources for us. So we need to understand that. We need to understand where it's cycling and how it's changing in a changing climate. What's kind of interesting is this chart here. This blue shows, so this is 90 degrees north to 90 degrees south. You probably can't see that in the back of the room. Blue liquid. The Tropical Rainfall Measuring Mission, which has been launched in 1997, only measures about from here to here, from 35 to 35, north to south. It's only really interested in looking at heavy to moderate rainfall rates, maybe down to, you know, a few millimeters an hour. The GPM core is going to go much higher, and so we're interested in snow as well. And then using all the constellations, we'll go pole to pole. So we're very much interested in taking the capability that we know about estimating rain from space to estimating snow from space. So in terms of water resources, Jim Foster and I, Jim, where are you? I saw you come in. Yeah, there he is in the back. If you remember, we had a very, very severe snowstorm back in February 2010. And so Jim and I got together with a bunch of other people and wrote a paper. And we wrote a paper in terms of, if there's satellite measurements, can you detect and estimate the snowfall rates? And what are they, and what are the errors inherent in them? And then after the snow is gone, what's left that's accumulated in snowpacks? And so Jim's area is in terms of snowpack. So it's kind of like how much water resources, how much snow water equivalent or water equivalent it is in that snowpack. So it's rather timely to look at that because we need to know how much melts off in the spring. Around here it melts within a few days. But in the west, you know, the Colorado River really relies on snowpacks from the mountains to feed it through the spring and through the summer. Okay, so if you'll take your snowflakes, if you have any cut, can you hold them up so we can see we all see what they look like? Ooh, nice. You want to pass the bags back and you want to cut. So if you were to take these and put them all on the ground, you'll notice that it makes the ground white. And what happens when things are white? Right? They reflect more. If you have a winter coat that's black, you kind of feel warmer because it absorbs the heat. It's the same kind of thing with snow. Okay, there we go. This is just showing snow cover through 2010, 2011. And you can see that as the snow covers in the winter, it gets whiter. The ground looks whiter and it's more reflective. When it's darker and the snow is melted, it allows the sunlight energy to be absorbed by the dark soil. And this is potential feedbacks for climate change. So we really don't want the snow. We want the snow to land and stay there for a while to reflect the sunlight. And we really need that aspect. Okay, so another component here is that we feel rain and snow in our backyard. It's a local event. But it's actually a driver of the global system. At the equators, there's uplift of the water from the oceans. The water gets moved to mid-latitudes. It's a way to transport energy, transport water. And so even though precipitation is local, it's a global mechanism for the Earth system. So we need to understand it for the energy and the water cycles. If we were to try to measure this from the ground, each one of these little yellow dots represents essentially a rain gauge. Rain gauges have openings of about this big, maybe 10 inches or so. And if you were to put them all together, they fill only about 2 basketball courts. So there's no way you can measure global precipitation with the rain gauges that just sit there on the earth. So we really need to look at it from a global scale. What we can use this data for is a bunch of different applications. These are all applications that the Tropical Rainfall Measuring Mission used, but we're planning on using them as well for GPM. So we can predict floods. If you know that 3 hours ago it rained 2 inches, and you're getting rain now and it's still raining at 2 inches an hour, you better call somebody to say it's potential flood here, unless you're on the top of the mountain and it's all running down. If it's all running down, landslide. You need to worry about landslides. So we're using all of this information to help us, with agriculture and famine early warning. World health. If you have rain, you might have mosquitoes. Mosquitoes might give you malaria. So these are all the different applications you can use in terms of rain, and there'll be applications in terms of snow as well. Okay, so how can we measure this? Okay, time for everybody to stand up and take your snowflakes. All right. So your snowflakes, we're going to drop them in front of you, and I want you to watch as they fall, okay? I'm going to drop my two too, if you don't have one. So you see how they kind of flutter? Some of they flutter around. So when you walked in, you may have seen these little GPM things, or some in the back if you want. This is the shape of a raindrop, a big raindrop. It kind of gets flat on the bottom, but they almost always fall almost straight down, okay? They don't change much. But the snowflakes, you see them wobble and fall and things like that. So rain is much easier because it almost always has the same shape. It's either round or it starts to get flat on the bottom. Snowflakes, as we saw from all of your cutouts, they're very, very different. So what happens is it makes it very difficult to measure them on the ground. So these is a radar on ground. There's no snow happening. But this is important. You see this little metal stuff here and the fencing? Those are all mitigating factors to try to keep the wind from blowing the snow, so that they really want it to fall into those little openings. And if the wind is blowing it, it'll never go into those because of aerodynamics. So they need these little fences. This fence, the fence around it, those fence. A lot of these other devices are rain devices. This is up in Canada, so they don't have the fences around them. We also measure via aircraft, and I'll talk about that as well. So we just had a field campaign up in Canada in January and February of this year, where we measured on the ground using all those measurements you just saw, devices you just saw. We had aircraft spiraling through the clouds, taking pictures of the cloud, temperatures, water vapor, and then we had an aircraft flying over the top that simulated what the GPM satellite would see. And it was very successful. That's just a very busy slide there. Some of the aircraft measurements, if you look over here, this was taken a long time ago, but up here at the very top of the cloud, the particles have defined shapes. When they start to melt, you see them start to clump together. So this is important. The satellite can't actually see individual shapes, but they can tell in general how big they are. And if they're all needles, we can kind of tell that they're all needles. If they're all dendrites, we can kind of tell things like that. So we need to know the different shapes. I was lucky enough to fly in the DC-8, and this is one of the instruments that was taking. The flights were whenever it snowed. So there was one flight, I think we left at 10 p.m. and we got back at 6 a.m. That's all part of the business. So, these are just some of the clues I put in my little magnifying glass. These are some of the clues to help us understand falling snow from space. Okay, one of the other things is there's no way in a cloud to be able to measure every single snowflake shape, size, amount. We have to use models. So these are some models that were generated in a computer. And we start with single one, then you add more and more, and and then you could get like grapple-like structures. So one of the things. We can use these snowflakes in three-dimensional models of clouds, and then compute what the satellite might see. Okay, you may be thinking, okay, computer. Didn't she just say she didn't want to sit in front of a computer all day? I sit in front of a computer a lot of the day. I also do a lot of physics, so I think my dad won. So anyway, it's part of the puzzle to understand what's going on here. So measuring snow from space. This is a little bit more about the trim. The trim only goes plus or minus 35, so it was only designed to measure rain. GPM is going to go much higher, where we get snowfall events and lighter rain. So the GPM core is going to come right up here in red, and it's because of its advanced instrumentation, we can use it to intercalibrate all these other sensors so you get the 3-hour coverage. Okay. Another thing that I did a long time ago, 2004, is this is work that my first paper after Jim Weinman said, hey, Gail, can you do snow? So this is the first paper we did, and we showed that if you have a very, very heavy snowfall, you can detect it using, at that time, it was a NOAA satellite. And because of this was why they added the high-frequency channels to GPM. These high-frequency channels, 166 gigahertz and 183 gigahertz, are particularly sensitive to the scattering signatures of snow. So these channels were added because of this work, and a few other people, NOAA people, Florida State people, and MIT people had all shown that you can estimate snow from space. So this is the GPM Core Observatory. This is a close-up picture of the spacecraft. It has radiometer, it's an imager. The way that I like to describe this instrument is that it's like taking an X-ray. If you went to the doctor, you could get an X-ray and it only shows your bones. That's all X-rays show, are basically your bones. This instrument takes an X-ray of a cloud. Because of all the different channels, the different wavelengths, it's actually an X-ray of about 2 different parts of the cloud. The liquid part of the cloud and the frozen part of the cloud. And I'm really oversimplifying it, but so we can use that to see the integrated quantity of where the ice and the rain exist, precipitating ice and precipitating rain. We also have radars which are underneath, and these are actually more like CAT scans. So your doctor will take a CAT scan, they can see layer by layer into your brain or your body. It's the same thing with this instrument. It looks at the sizes of the rain or the snow and the number of particles essentially at that size bin. So using the X-rays and the CAT scans of these instruments, we can tell what's happening in a cloud. We can look at the processes within the cloud. We can use that information for modeling later on so that our forecasting models and our climate change models would be better. So we're pretty excited about that. Okay, so this is a little video. And Ryan, who is the GPM, he's our filmer, he's our producer, he makes all of our films. He did a great narration based on my words, but I can't narrate like this. And I'm going to play this.
In addition to measuring a wider swath of the globe, the GPM Core spacecraft will carry more advanced instruments with greater sensitivity. There's the GPM Microwave Imager, or the GMI, a radiometer that will use 13 microwave channels to capture precipitation intensities and horizontal patterns. Then there's the Dual Frequency Precipitation Radar, or the DPR. That uses 2 frequencies to visualize in 3D the precipitation structure from the cloud down to the surface.
Okay, these are just some of the images of the spacecraft. This is the radar being lowered onto the instrument. And as I said, this is being built right now at Goddard. It's the largest spacecraft to be integrated and tested at Goddard to date. You can see there's a person down here. This is up and down. These are the radars. So the Earth would be coming out of the plane there. The radars look directly down on the Earth. We just finished thermal vacuum testing, so they put it in this big chamber and they suck out all the air, so it's like the vacuum of space. They change the temperature to make sure that the spacecraft works in that environment. In October, we send it to Japan. Japan's actually going to launch it. They have a launch site on one of their islands. It's just like our Kennedy Space Center. You talk to any Japanese, they know exactly what you're talking about when you mention that island. So we're very excited about the fact that it's here. Occasionally we do go over and take tours of it and show people that. I don't know if we'll do one anytime soon. Okay, so in terms of my work, I've kind of alluded to some of the things that I do. First and foremost, I'm trying to interpret the measurements that the satellite has to what's snowing underneath, and we call those retrieval algorithms. So I'm taking the measurements from the GMI and the measurements from the radar, from the radiometer and the radar, and putting them together to get estimates. And I'm not going to go into the details. It's a Bayesian algorithm. It's already been delivered to the data processing center. We are doing more testing. There's a whole production line of computer programming steps and deliverables. So very excited about that. One of the other things, Joe Munchak and I, Joe, are you here? Yeah, Joe's here. One of the things we wanted to do, because early on retrievals showed that we could estimate very heavy snowfall rates, it's what's the lowest snowfall rate that we can see with the GPM instrument. And basically we got down to about 0.5 millimeters an hour melted. Now, a melted rate would need to be multiplied by 10 or 20 to get the fluffy rate. So we're looking at 1 to 2 centimeters an hour. It's still a pretty significant snow for us to be able to see it. Now CloudSat actually it's a different NASA satellite. It can see the lighter snowfall rates. So these are two papers that are been accepted, about ready to appear. I have one more video I want to show you. You kind of heard me mumble through my presentation with lots of ums and starts and stops. This again is one of Ryan's productions, and I like to call this GPM Hollywood style because this is the best of the best. Everybody's slow, they're calm, they make their points, the pictures are pretty. I don't think this will win any awards, but I still really like it, so let me start this up.
Only 3% of water on Earth resides as fresh water, and only a tiny fraction of that is actually accessible to us on the surface.
7 billion of us live on this planet. We all have to drink water to live. Where's the water that we drink come from? By and large, precipitation.
GPM is an international satellite mission providing a new generation of observations of rain and snow in all parts of the world every 3 hours.
If you have good precipitation information, you can do a very good job of characterizing drought and often its subsequent impact on agricultural productivity.
There's about 1 major flood a day someplace in the world. So it's not as if it's a rare event.
Understanding how much snow is falling is important for transportation, safety, how much fresh water falls and is stored in snowpacks. But we really need to focus on all the phases of precipitation so that we know the global picture of where fresh water exists in the Earth system. So I have to say, we do have some very creative education and public outreach people that are helping us with science writing, with making these videos, and I think it makes a difference. So I'm very grateful to have a good team to do that. In my abstract that was widely broadcast, I said I'd talk about why scientists love and hate snow. So at the top are some reasons why we really hate it. You know, it's a really hard problem. Those raindrops, they're so simple. Oh my gosh, they're so simple. I'm so jealous of all the precipitation people. Snow is so much harder because every different shape, you know, it matters if the surface is already snow covered. It almost looks like the snow is falling, so it's like mind-boggling. But We've done it, we can continue to do it, and we continue to improve it. Okay, I already talked about a little bit, we can't detect all ranges of snow from the very, very lightest to the heaviest on one platform at this time. You could put CloudSat and GPM together, but that's too expensive. You could design new technology. We're not there yet. We're about 40 years behind rain estimates. The first rain estimates from space were in the 70s, early 80s, and they probably had worked on it for 10 years before that. So we're behind. But that means, hey, I got a career for the rest of my career. I can work on that. A next generation, and maybe the generation after that can work on this. It's very, very hard to forecast snow, especially in this region. I am not a meteorologist, I'm an engineer, but I know that around here, the rain-snow line changes, the weather patterns are affected by many different things, so it's very difficult. Some of my friends, you know, my kids' parents, they find out I'm in snow, they say, oh, is it gonna snow tomorrow? And I'm like, I don't know, give me 20 years and I'll tell you and give you a better forecast, because we just don't have good forecasting. But with GPM and the data we get from GPM, well, we can improve those weather forecasts. Okay, I love snow, it's beautiful. I mean, let me see all your snowflakes. I want to see your beautiful snowflakes. Yeah, very nice. Please take those home with you. What I'm doing is cutting edge research. As I said, there's probably only about 100 people worldwide that are doing falling snow estimates. Snow on the ground, I don't know, Jim, I'm sure it's a larger community, but it's just great to be out in the front. Everybody's interested in it. We get to go to great locations for field campaigns. I've actually not been to the polar regions, but there the snow is like diamond dust. It's really, really hard to estimate. So I'm actually looking for where you get the nice, pretty snows. Although I have to say, my colleagues that do tropical precipitation, that come back from spending a month on an island near the equator, yeah, maybe they've got an edge on me there. I really like the fact that we're able to solve one more piece of the Earth cycle puzzle. You know, over the years, we've been framing the puzzle, putting the edge pieces in, but until we understand how snow relates to liquid precipitation, how it relates to the water cycle, how it relates to the energy cycle, we really don't have a full picture of the Earth system. And I feel like I'm contributing to that, and that's one of the reasons I love doing this work. And, okay, let me take a show. How many people like snow? Okay. How many people like rain? Okay, so the numbers are different. I don't know what it is about snow, but I love snow. I think maybe it's because it's so bright and light. And, you know, people that have seasonal, you know, darkness thing, when it snows, it makes everything brighter. I like the snow. I like the rain too, but I much prefer to go out in a snowfall event.
It's quiet.
And snow is quiet. It doesn't make any noise. Yes. Yeah. So that's all I have, except for one last slide to close. Well, I guess two last slides. If you want more information about GPM and the work we're doing with snow, the website is easy, gpm.nasa.gov. And my education and public outreach friends have told me that I'd be in deep problems if I don't mention that we have a photo contest going on right now. They're taking photos until February 4th of any kind of winter weather. If you're one of the lucky ones that lives at the equator on one of those islands, take a picture of yourself in a bathing suit, send it to us. These pictures are going to be used in future GPM education and outreach. And I think there's some small prize, yeah, GPM trinkets. You'll get one of these. And then I just have, you know, a listing of some of these papers that I showed here, and then I'd be happy to entertain questions. Oh, very good. Thank you. I completely missed that. GPM is going to launch in February 2014, so we're about 13 months away. So when we ship it to Japan in October, it takes, I don't know, maybe a month to get there, and then they have to put it on the launch vehicle and get it all set up for launch.
Is it going to snow tomorrow?
Ask me in 20 years.
Ask in 24 hours.
Yeah, for me, what I do is I look about 6 to 12 hours in advance to the, whatever weather, your favorite weather channel thing, because around here it's just so hard. Yeah.
So how is GPM going to get to Japan?
Okay, so this is one of the interesting stories. The question is, we have it here now, how is it going to get to Japan? We're going to fly, we've made a deal with the military, it's going to fly on a C-5 jet. The interesting thing about the C-5 jet is that the military want to use this as a training exercise, so it's going to be refueled in flight. They tell me it's not risky. I think what happens is that they have the trained pilot, and then they have the observers that are watching. So it'll be refueled in flight, and then it lands in Japan on the big Japan island, put on a ferry, and the ferry will take it back over to the island. It's just too big to put on a regular plane, and it would take too long to put it on a ship. Yeah.
How much is it costing to build it, and is Japan paying for part of it?
Japan is paying for part of it. They're building the radar, and they're paying for the launch. To pay for it here, it's about 3 water bottles, $3 per U.S. person. So it's just under $1 billion, 940 or something like that. Yeah.
Can you talk a little bit more about your findings from the Canada Snow campaign and maybe talk about the next field campaign that's coming up?
So during this field campaign that we had in January and February, we went up to Canada. We'd already been up to Canada in '06 and '07, so we knew we had a good partnership. And as you saw in that video, they have lots and lots of instruments to measure the snow on the ground. We had about 26 flights where we measured snow. We measured everything from liquid rain to rain that was freezing, to mixed phase, to heavy snow, to light snow, all sorts of events. We had some lake effect events where they got 10 inches, 20 inches. So we're going to use all that data to try to interpret in between the measurements on the ground, the measurements with the aircraft looking at the actual particles and above. And we're going to look towards some future field campaigns. One of the next ones we want to do with snow is not till 3 or 4 years out. We're going to go to the Olympics region outside of Seattle where they have mountains. And so you'll have the snow at the top, and then you can put instruments all the way down the mountainside so you can see the transition from snow to mixed phase to rain. So that's one of the things. There's also other field campaigns that GPM is doing that are related more like water basins. So it rains, and then you check the stream flow. So but that's not related to snow. But we're doing all sorts of field campaigns. Yeah.
You mentioned that you're going to do tours of this.
Yeah, we'll have to probably set something up. Yeah, I mean, if you're interested, either shoot me an email and we can. That's probably the best way to do it. I'm gail.s.jackson@nasa.gov.
Or you can email the website.
Or the website. Go to the website, and there's a contact form, and we'll set up something for you. Yeah.
Many people who grew up in Maryland, they remember and claim that almost all Christmas or New Year Eve were white. And so for 20 years I've been in this area, it was just a few years. So do you have Maryland statistics about white Christmas, New Year, January, and so how?
I don't have those at the tip of my fingers, yeah. It's got to be, there's changes. El Nino, La Nina affect the weather patterns. The North Atlantic Oscillation affects the winter patterns here. I'd have to Google it. I don't know. I mean, Jim, somebody else, do you know that? Yeah? No? Okay. Yeah, Wayne, yeah. Yeah.
How long does it take a snowflake to form? And for most of our snowfalls, how high is that coming from?
Oh, okay. So it doesn't take very long for a snowflake to form. Probably minutes, maybe an hour. Not an hour, minutes. Snowfall events, lake effect snowfall events, like the ones that come off the Great Lakes, they can only be a kilometer or two. They can be very, very shallow. a kilometer or two, and yet they can deposit a lot of snow. One of the ones that we just measured in January and February had 20 inches, and the cloud tops were like 1.5 kilometers. So they're just full of liquid, and they just dump the snow. Others are much higher. What we have found with GPM, the taller cloud tops, it's actually easier to know that you've got a snow event because the way that the instruments work, they can tend to see higher cloud tops. When it's really shallow, you have a hard time distinguishing between the clouds and the surface features.
Any more questions? If not, let's thank Gail once again.
If you have scissors, leave them on one of the chairs back there because my family would be mad if I don't bring home my scissors.